Hey everyone, just wanted to do a quick video here on the rational zeros theorem. And this one we're going to do slightly differently than maybe you've seen in some other videos. Um, a lot of people like to use this to find zeros, and sometimes it's good and sometimes it's not totally necessary. So we'll kind of talk about that a little bit here. So first off, what does the rational zeros theorem say? So if you have a polynomial, we'll say p of x is ax to the n and then a bunch of other x terms plus c, right? And we're assuming all the coefficients in front of all the x terms are integers. So a is an integer, meaning like a whole number, but you could have positives or negatives. And also all the other x terms, right? They don't have fractions, they don't have roots, they're all integer values, all the way down to the constant at the end. So if that's your polynomial, then any rational zeros have the form of that x would need to be a factor of c over a factor of a, right? So a factor of that constant at the end over a factor of the leading coefficient. And there's a few different questions you can get asked. One is list the possible rational zeros, right, for any given polynomial. Another one might be, to actually find the rational zeros from that list. And so we'll kind of go through, or find all the zeros, but start with that list is another way. So we'll go and start with just list the zeros, right? That'll be our first thing. Just list the possible rational zeros. So I have four functions we're going to talk about over here on the left. We're going to start with this x cubed minus 21x plus 20, right? So what I do is I would say my x's have to be factors of 20, which is my constant, over factors of 1. And the factors of 20, right, are all the things that multiply nice to give me 20, all the integers. So that would be, I could have a 5 and a 4, or I could have a 2 and a 10, I could have a 1 and a 20. So those are the things that I'll multiply to give me 20. So I'll go ahead and list those out. These all have a plus or minus in front. So plus or minus 1 would go, 2 would go. I think the next one would be a 4, 5, 10, and 20. Right, all of those either plus or minus could be a possible rational zero, right? And then we'll go ahead and divide by all the factors of that lead coefficient, which in this case is just 1, right? So we have that kind of 1 in front of the x cubed. So this would be just a plus or minus 1 at the bottom. So really, when I divide all those numbers by 1, I just get themselves. If I divide by -1, they'll have the negative. They already have a negative if I need it anyway. So really, this list is just going to be that whole thing, plus or minus 1, 2, 4, 5, 10, or 20. Right. So that is my entire list of the possible rational zeros. Now, what do I mean by rational zeros? So rational zeros, that means any zero or root, right, place where I cross the x-axis on a graph, that can be written as a rational number. And a rational number is basically just a fraction, right? So like 1/2, 2/3, 4/5. I'm not including roots. I'm not including things like pi or, square root of 10, any of that sort of stuff. So just a integer over integer as a fraction. So basically these are roots that are either whole numbers or fractions. So this is my list right here. And then what some people will do will say, all right, go ahead and find all the zeros. All right, so find, so these are possibilities, right? Possibilities. Say possibilities, see if I can spell. And then you might say find the actual zeros, right? Find the actual from that list, right? This is a cubic, so we know at most there's going to be 3 zeros. That is a way bigger list than 3, so only 3 of these at the most would work. So find the actual zeros. Might be a next step that you might want to do. And there's a couple ways to do that. One is to go through one by one and kind of test, right? If 1 is a 0, then x minus 1 is a factor, and I can plug in, see if it equals 0. I can try to divide it out, see if it divides out, right, with long division or synthetic division, the factor that matches with the 0. So any of those techniques might work, but you can also just graph it, right? And this is kind of a theorem from before you actually had technology to graph. So people would actually, try to build a graph based on this information. So that this would be kind of a starting place. If I didn't have a graphing calculator, if I didn't have Desmos, if I didn't have any technology whatsoever to actually make a graph, this would be a great place to start at finding the zeros, right? Would be, these are possible, right, nice numbers that could be zeros. And then maybe I test a few of these, right, go through and test those to see which ones actually are zeros. Since we do have some technology, I'm going to go ahead and just graph that function there, and then we'll take a look. So it looks like -5, 1, and this other one here. See if I can get that one as well. 4, right? So those are my actual zeros, and let me try that again. -1 and 4. So -5, 1, and 4, which we can see are on the list. So -1 is on the list. 4 is on the list, and sorry, not -1, -5 is on the list. +1 and +4. So those three are the actual zeros, and they are in the list. Now, sometimes for really nice functions, all the zeros will be rational zeros. That doesn't have to be the case, but if I've got all three, right, at the most I can have 3 because it's a cubic, so that would be it. I'd be done. Those are the actual zeros, and I'm done. We will see a couple examples here in a second of where that maybe doesn't happen, but that's always your best case scenario. So any rational zeros that you can find will show up on the graph. They may be listed as decimals on the graph, but they will be on the graph, and you can use that list of possibilities to kind of narrow it down into what fractions will work. All right, let's go ahead and try another one here. So I'm going to hide that one. Let's try, let me see if I can get the whole polynomial here. Find a possible rational zeros for that second expression right there. So rational zeros. All right, possible rational zeros for y is 6x to the 4th plus 5x cubed minus 36x squared minus 25x plus 30. So this, again, we're just kind of focused on, right, this constant and this lead coefficient, those two numbers right there. So the possible rational zeros would be factors of 30. All right, so I'm going to put factors of 30 on top over factors of 6. And we'll go and list them out, right? So we'll go and list these out. So we would say, let's see, factors of 30. That's going to be, I'm going to list a few up here. So we got 1 and 30. We got 2 and 15. We got 3 and 10. This is going to be a long list. And we got 5 and 6. All right, so I'm going to go ahead and put those in order. All right, so we got, let's put a plus or minus in front. So plus or minus 1 looks like 2, 3, 5, 6. We also have 10, 15, and 30. So quite the list on this one. And then that's going to be divided, right, by factors of 6. So plus or minus factors of 6 are 1, 1 and 6, and 2 and 3. So I'll just say 1, 2, 3, and 6. Now what I need to do, right, is actually divide all those out. And so this can get really long, especially on ones like this where there's lots of factors, right, on the top and on the bottom. This can get to be a pretty long list. And then we'll take a look at what factors might actually work, right, next. So let's see. So this would be all of the whole numbers, right, over 1. right? So we can just go ahead and list those out. So we'll say plus or minus 1, 2, 3, and I'm not writing the plus or minus with each number. Just keep in mind, all of these are considered to be either positive or negative. All right, 6, 10, 15, and 30. All right, divide all these by 2. Now, some of these may end up being repeats, like 2 divided by 2 is 1, and I already have the 1, so I won't have to list that. But we'll go ahead and put in anything that I don't already have. So 1 divided by 2, that'd be a 1/2. Again, plus or minus. 1/2, 2 over 2, I already have that as a 1. 3 over 2, I do not have, so 3 halves. 5 halves. 6 halves is a 3, and I already have a 3. 10 halves is a 5, I already have a 5. 15 halves, I can put that. And 30 over 2 is 15, I already have that one. Okay, so the 2 is done in the denominator. The 3, right, so 1/3, I don't have that. So we'll say 1/3. 2/3, I don't have that. 3/3 is 1, I already got that. 5/3, that's a new one. 6/3 is 2, so I already have that. 10/3, that's a new one. 15/3 is 5, and 30/3 is 6, and I already have both of those. So that's all the ones with denominator 3, and the last one, denominator 6. So we got 1/6, which is new. 2/6 is a 1/3, which I already have. 3/6 is a 1/2, which I also already have. 5/6, that's a new one. I got 5/6. 6 over 6 is 1, already got that. 10/6, that'll reduce to 5/3, and I already have 5/3. 15/6, that'll reduce, let's see, to a 5 halves. I already have the 5 halves. And 30 over 6 is 5. So that's actually it for the denominator 6. Whew. All right, so that is my big long list of possible rational zeros. Now we started with a 4th degree, so at most only 4 of these are actually going to work. And then the next step, right, if I actually wanted to find the rational zeros, we'll put in parentheses actual, right, the ones that actually work. Then I would need to start again plugging those numbers back into my polynomial and seeing if they actually do equal 0, or try a synthetic division, right, that matches, divides the factor that matches with the root, or something to that effect. That's going to take a really long time, right? So anytime you have to go through those by hand, that is going to take a very long time. We are going to shortcut it, right? So I'm just going to graph this guy, and expand this graph a little bit. So I'm interested, right? Here's what my graph looks like. 4th degree has kind of a peak up here somewhere. It's got a valley down here, but the zeros, right, always along the x-axis. And it looks like I have that -1, 5, this 0.6 repeating, right? So those decimals are actually fractions, right? They don't terminate, or they do terminate, or they repeat, right? So -1.5, that's the same as a -3 halves. So I'll go and write that one down. So -3 halves. The 0.67, right? This is a 2/3, right? So 2/3, same as 0.6 repeating. These other ones here, right? This -2.3607, that is not going to be on the list. So 1/6 and 5/6, those aren't going to match. All the other fractions, those aren't going to match. So this one is what we would call a 0, but it's not a rational 0, right? This is going to be something that involves a root, right? So it's a real 0, but not a rational 0. To get that one, you would actually need to divide out the factors that match with this, right? So there would be factors like maybe x plus 3 halves, or you could even put like a 3x minus 2, right? Judging from that polynomial, it had a 6 in front, so we could probably divide that out, and there would be another factor from the 2/3 that would be, actually I think I got that backwards. Let me do that again, because 3/2 would not solve that guy. This would be a 2x minus 3, or plus 3 for this first factor, and then the other one would be, you could say an x minus 2/3, or even a 3x minus 2. Right. So those would be factors that match up with those zeros. You could divide those factors out with either long or synthetic division from that 6x to the 4th polynomial. What you would end up with is a quadratic, and then you could factor the quadratic. You would get some sort of roots, like I think this one ends up being negative square root of 5 and positive square root of 5. But that is a process that you'd have to take to get down to what we call these irrational roots or irrational zeros. All right, so finding these zeros is sometimes useful, right? If I need exact values, right, not decimals. Finding some of these rational zeros can definitely help eliminate some of the factors and then get down to quadratic, and hopefully use quadratic formula or something like that after that to get the rest of the zeros that don't show up so nicely as rational zeros because they're irrational, they involve roots, and they're just not able to be written as a fraction, at least not with whole numbers. Some other things that can pop up sometimes, we'll go ahead and try another one here. So this is, let me go ahead and try to expand that out. 15x to the 4th plus x cubed minus 62x squared plus 4x plus 8. Again, you could find the rational zeros and figure out which one of those are real zeros, right? So we'll go ahead and run through that real quick and then make a comment on the one that comes after that. So I'm going to go ahead and clear this screen. I'll write a few things down just so it doesn't take up so much time on the video, and then we'll come back here. All right, for this one we have find the possible rational roots for 15. This should be x to the 4th plus x cubed minus 62x squared minus 4x plus 8. I'm going to make that 4 a little bit clearer. Possible rational roots, right? You're going to take those factors of 8 over factors of 15, right? So we got the plus or minus 1, 2, 4, and 8, and 1, 3, 5, and 15. And then I go ahead and list them all out. And this is the big mamma jamma list that I get, right? So we actually don't get any cancellations, no repeats with this. So all the 1, 2, 4, and 8 over a 1, over a 3, over a 5, over 15. There are no repeats, there are no cancellations that give me values that were the same like it did last time. So it's just a big, huge, long string of numbers that are right there. If we want to find the actual zeros, right? Find the actual zeros that are rational, right? So again, we're kind of leaving some of the other ones for a little bit later here, but finding the rational zeros, right, would mean testing all these, right, by hand, hoping that you get to the ones that work sooner rather than later, or you can go through a graph, right? So we got the graph over here listed in Desmos, so I'm going to go ahead and try to zoom that in a little bit. So we got -2, negative 0.4, 0.3 repeating, and this last one, which can't seem to get to work. Let's try this. There it is, 2, and there's the 0.3. All right. So this -2, right, that's easy. -2, negative 0.4. Let's see what that might match in our list. So it's going to be negative. That would be a 4/10 or a 2/5, right, if we reduce it. So negative 2/5 would be another rational zero. The 0.3 repeating, right, that's going to be a 1/3, positive 1/3. And then the other one is a 2, right, so that 2 is going to be positive 2. There's only 4 zeros here that we could possibly have because we have degree 4. You can't have any more zeros than your degree. So those would be the actual zeros, right? So again, this list, if you already know your decimals, right, and you weren't asked for the list and you just wanted to find the zeros, you could just shortcut it, right, not write the list out, go straight to the graph, write those out. Sometimes if there's weird numbers that happen, it's nice to have the list to see, oh, what could those fractions be? Or maybe like the last one, they aren't fractions, they're ones that involve roots. So sometimes that list can be kind of handy if you're not sure about what kind of fractional possibilities you might have. This last one is just another quick example that we'll go through, and I just have to change a couple things. I'm just going to change those over here. So the list is actually going to stay the same, right? So this list I'm just going to leave up, and we're only going to change this middle number here. So this is now a plus 58. Instead of a minus 4, it's a plus 4. And instead of a plus 8, that's going to be a minus 8. Right? So I'll change that plus into a minus. The rational roots would still be factors of 8 over factors of 15. So still the same list, still the same huge list over here of possibilities. If we look at the graph, right, this time I only see 2 zeros, right? So this one at negative 0.4 and this one at 0.3 repeating. So that's the negative 2/5 and the 1/3. So negative 2/5, 1/3. And looking at all the other numbers that are on here, right, I don't see any of those. But notice, right, this 8, that's kind of our biggest number, right? So if I don't see anything in between, by the time I get to 8, it's just not going to happen, right? So we can take a look, right? And it looks like this graph is just going to keep going up forever. It's not really going to come down, at least not and give me a rational 0, right? And anywhere between that negative 10 and 10. So all of our list is contained between the negative 8 and the 8 for these guys. So so no more rational zeros, right, are going to appear in there. And you may be wondering, like, it's a degree 4. A lot of times you will have that same number of zeros, but the extra 2 zeros I'm missing, these are actually going to be complex number zeros. So I'm just going to say for now, too complex. All right, that's all we'll say for now. We will actually find those later in the course, so there'll be a separate video and separate thing to do last time, or in the future here, but it'll be kind of the same deal, right? We'll have to list the factors, divide them out, kind of get down to quadratic, and see what I can get after that. So so we will get to some more of these, finding the complex zeros. That'll just be a bit later. So for now, we're kind of focusing on these real zeros. That'll kind of do it for this video. Some things that'll come up a little bit here are if I have an equation, or if I have a polynomial graph, right, finding the equation off of that graph, and it'll kind of involve this idea of the roots and factors relating to each other, and then also looking at some polynomials with the graphing project. So, but hopefully that helps you with the rational roots theorem.